Okay, we are continuing on here, chapter 14. And last time we got into acids and bases. And a reminder, an acid is something that can produce H plus ions in solution. And when we talk about that, we're talking about the ability to produce in a solution free floating, basically H pluses. Remember as well that H plus and H3O plus are essentially the same thing here in acid-base chemistry. One is the hydronium ion, one is the hydrogen ion, and they basically mean the acid part of the solution, and you can interchange them in formulas and also equations as well. The base is something that will produce hydroxide ions in solution. And again, same idea. Basically, we are going to be producing free floating hydroxides in that solution. A more sort of general definition of an acid base is the one that most people look at is the Bronsted-Lowry definition of an acid and a base. In the Bronsted-Lowry definition, an acid is a proton donor, so somebody that will give away an H plus, and then base is a proton acceptor. Again, H plus is also referred to as a proton as well. What we talked about with that is also the importance of the positive charge here. Again, that does change the charge on whatever is gaining or losing that H plus as well. The sort of consequence of the Bronsted-Lowry definition of an acid and base is it does create partners sort of on the other side of the arrow where we have conjugate acid and conjugate base. And the acid on one side is related to the conjugate base on the other, and the base on the one side is related to our conjugate acid on the other. Basically, our regular old kind of acid and bases are usually found on the left-hand side of the arrow. Our conjugate guys are found on the right-hand side of the arrow. And the only difference that it can be is really what happens in the situation, which is the acid donates that H plus over. So it could only be one H plus difference in order for those guys to be pairs. So with the acid to the conjugate base, we'll have one less H plus as it gets rid of its H plus. And as we go from the base to conjugate acid, it'll have one more H plus as it accepts the H plus. Again, if there's any more difference than just one H plus, they are not considered basically pairs. As we saw last time, things have more than one H plus they could give off. They actually do come off one at a time. So again, a difference of two H pluses does not make them partners either. It has to be only one. We talked about the autoionization of water, and water can react with itself. And one would be an acid and one would be a base. And again, we'll have this sort of situation happening. And it will actually set up an equilibrium in solution. And you'll have this here plus a little OH minus. Once again, you could do H3O plus and OH minus as well. Since this is an equilibrium, we could write an equilibrium expression for it, which is known as Kw in this case. It is the same thing as normal products over reactants. In this case, since our reactants is water in the liquid state, it would not be included. And for the most part, this is a constant number of 1 times 10 to the minus 14. Although, again, as we know from our equilibrium discussion, it is an equilibrium constant. So technically, it does change with temperature, but pretty constant. That number is most of the time the one you're going to probably use 99.9% of the time. What this allows you to do is you can obviously solve this, and it's really the same calculation regardless of which one you're solving for. You're going to take the concentration you know and divide it, take the 1 times 10 to the minus 14 and divide it by the concentration you know to get the other concentration. So it's really the same sort of calculation there. Again, you could compare them. So if the H plus concentration is larger than the OH minus, that basically means your acid part is bigger than your base part. It will then be an acidic solution. If the H plus concentration is equal to the OH minus concentration, then you have a neutral solution. And if the H plus concentration is less than the OH minus or greater than the OH minus, then it will be a basic solution in this case. Again, this is another one where you could, if you want to, obviously use H3O plus there instead of H plus, but it's basically the same. Any questions on any of that? Thank you. All right, so I think we did an example at the end last time, so let's continue on here. So I think we're at this example. In a solution, a particular H plus concentration is 1.2 times 10 to minus 6. What would be the hydroxide concentration? And is the solution acidic, basic, or neutral? So give it a go. Let's see what you come up. So good news, like I said, it pretty much is the same calculation regardless of which one you are given. 1 times 10 to the minus 14. So in this case, we do have the H plus, so we will solve for the OH minus, which will be 1 times 10 to the minus 14 divided by our 1.2 times 10 to the minus 6. Definitely want to be using our exponent button in this chapter for sure. Going to give us an 8.3 times 10 to the minus 9. It does need molarity as it is a concentration. If you are not in scientific notation, then you probably had like 8 zeros and an 8 at the end of your calculator, and you ran out of room. So, if you were maybe not in scientific notation, you had a bunch of zeros, about 8 of them, and then just an 8 at the end. And if you go scientific notation, that's how we obviously get to here. That chooses these two here in terms of possibilities. We then want to compare basically our H plus concentration, which is our acid part. So here's our acid part, which is our H plus, 1.2 times 10 to the minus 6 molar. So we want to compare the H plus concentration to the OH minus concentration. And in this particular case, which one is larger? It is the H plus concentration is larger, right? Remember that when you're comparing negative exponents, the smaller negative exponent is the larger number. As -9 means we're going 9 places that way, and putting zeros, we're only going 6 places that way and putting zeros, so it's a larger number. So it looks like number 4, I think, would be the winner there. Any questions on that there? All right. So then let's talk about pH, and pH is a measure of acidity. And the pH scale does run from 0 to 7 to 14. Less than 7 is acidic. Above 7 is basic. And really dead on 7 there is neutral. And dead on 7 is neutral because the concentration of H plus will equal the concentration of OH minus, and they both will equal 1 times 10 to the minus 7, which will give you a pH of 7 exactly. So we will go for neutral being exactly 7 or super, super, super close to 7. If it's a little above 7, then it will be considered slightly basic. If it's a little less than 7, it'll be slightly acidic. It needs to be really, really close to 7 to be neutral. The formula, or actually when we start at 7 and go towards 0, we're becoming more acidic. When we go from 7, head towards 14, we're becoming more basic. And to calculate the pH is equal to negative log of the H plus concentration. So this, once again, is also another one that you could swap out the H plus for the H3O plus, same thing, whatever you like there. Now, obviously, if we have a neutral solution, the concentration of H plus equals the OH minus, we'll have an H plus concentration of 1 times 10 to the minus 7 and a pH of 7. If you have a greater H plus concentration, your pH will be less than 7. And if you have a greater OH minus concentration, then your pH will be above 7. So as the concentration of H plus goes down, the pH goes up, and vice versa. The more H plus you have in the solution, the lower the pH will go. And that is really for the relationship we talked about last time, which is as the H plus concentration goes up, the OH minus concentration goes down, and vice versa. As the H plus concentration goes down, the OH minus concentration goes up. So they run opposites of each other. So when you have a lot of H plus in the solution, you have very little OH minus. Is going to be a very low pH because it's going to be really acidic in that solution because you have a lot of free H plus basically floating around, and vice versa. If you have a lot of OH minus in that solution floating around freely, the H plus concentration is going to be really low. So it can be very basic because of all that free floating around OH minus. So let's talk a little bit about calculation, how to punch these in properly, just in case. If you have a display calculator, you would punch it in exactly the way it's written, which is you would go with your negative button, you would go with the log button, and you would go with the concentration of your H plus, probably using your exponent button. You have a non-display calculator. This formula and pretty much the rest of them here in this chapter, you will have to kind of work backwards. So if you have a non-display, you actually got to start with the concentration using your exponent button. You then need to hit the log button, and then you need to hit the negative button. If you're not sure what type of calculator you got, you could just hit the log button. And if it says log on your screen, congratulations, you have a display calculator. If it says error on your screen, congratulations, you have a non-display calculator. So that'll be a quick way to figure out how to do that if you're not sure. So make sure you know how to punch it in properly when you go for it. Now, when we talk about pH, we also want to talk about pH and sig figs. So the number of decimal places in your pH type of answer will equal the number of significant figures in your concentration. So the number of significant figures there are in your concentration that you're going to calculate the pH or whatever it may be, will be how many decimal places you should take it to. So let's just try one here. Let's take an H plus concentration. We'll go 1.2 times 10 to the minus 6. That's our pH equation here we want to go with. So again, depending on your calculator, if you have a display, you would punch it in once again. In this case, your negative button, you would go 1.2, your exponent button, your negative button, and 6. And you would actually hit the log in there somewhere between that there. Just squeeze it in there. Missed that wrong one there. Put the log in there first, and then you hit that, and then you hit equals. Non-display, you would actually go 1.2. You'll hit your exponent button. You go your negative button, and you go your 6, and then you'll hit the log button. Doing the last one first, and then your negative button one more time. And if you do that on your screen there, you should get 5.920818754 in terms of the pH. Now we want to get this to the right number of digits. I should take this to 5.92 in this case. That is because this number written in scientific notation has 2 significant figures. And that gives me not 2 sig figs here, but 2 decimal places. So it is significant figures to decimal places in this case, not sig figs to sig figs or anything like that. Any questions on that one there? By the way, that would be obviously acidic, yeah, as it's less than 7 in this case. Yeah. Any questions on that there? All right, let's take a look here. We have our pH scale here. As I mentioned, we have a strong base, which is up there at 14, strong acid down there at 1. We have blood, milk, some pure water. We have obviously some vinegar, some acids, some household cleaner sort of happening. If you take water that's not pure water and just our water has been out for a while, the pH would actually be probably like in that range, just be acidic as it picks up some CO2 from the air and makes some carbonic acid, has increases the H plus concentration, lowers the pH and stuff like that. Sometimes people are surprised at that. This is not always 7, especially if it's been sitting out for a while. There is another scale that is similar to pH, and that is the POH scale. And the POH scale is measures exactly what it says. POH means you need the OH minus concentration, and it's calculated kind of the same way. You take a negative log of the OH minus concentration, just like pH is obviously the H plus concentration is what you would use in this case. The reason that could be very helpful for you, for example, is if you have the OH minus concentration but want the pH, you could actually calculate the POH and then use this relationship here, which is the pH plus the POH is equal to 14. So that does give you a little bit of variety in terms of how you could solve it. If we add in our guy that we saw earlier, our KW that we saw previously here, there's another guy that gives you some ways to do it. So if you have the OH minus concentration, again, you can calculate the POH and take 14 minus it to get to the pH. You could still use KW like we did earlier. You could take the OH minus and convert it into the H plus and then go into the pH equation. So you do have a few different ways. They all should give you the same thing. This is a pH meter down here. It's an electrode, basically works off of voltage. You calibrate it for 4, 7, and 10, like you'll do in some experiments coming up. And then it makes like a little calibration curve and go, oh, your voltage is here. So that's like a pH of whatever it may be. And it gives you a digital display made by a guy named Beckman over there in Fullerton. And was one of the first sort of commercially used pH meters that was used. A couple other things that we'll add to our list here of sort of calculations that's sort of helpful is if you have the actual pH, you could get directly from it the H plus concentration. So if you have the pH given to you, you could calculate the H plus directly from it. The H plus concentration in that case will equal the inverse log of the minus pH. And on most people's calculators, when you do the inverse log, that is the one that pops up like a 10 and a caret on most people's calculators. And you want to make sure it's negative pH there. And that's usually what it'll kind of look like on your calculator. To get to that, by the way, on most people's calculators, second, our shift button on the top left of your calculator. And usually the log button will have a button like that. That is the inverse log, or how most people use it for scientific notation incorrectly. So that is what you want to use it for. Just like pH, if you have the POH, you can directly get from it the OH minus concentration. And the OH minus concentration is equal to the inverse log of the minus POH. So it's really the same calculation. And again, on your calculator, 10 and negative POH. So this does give you a variety of ways you can really solve these problems depending on which path you want to take. And they all should really get you to the same path when it's all said and done, or the same answer when it's said and done. So if you have the pH, you can get the H plus concentration. You have the POH, get the OH minus. If you want to calculate the pH, you need the H plus, and if you want to calculate the POH, you need the OH minus concentration. So the name basically tells you what you need to calculate those things. Any questions on any of that there? Now, just like display, non-display for these formulas here, you also need to work either forward or backwards depending on the type of calculator you got. So if you have a non-display calculator, you need to put the number in first, make it negative, and do second log. You have a display calculator, you go second log and then negative and then the number. So it kind of works the same way, depending on how you put it in. Now, really important thing that we just talked about, which is the pH scale, which is 0 to 7 to 14. And again, this obviously being neutral, and below 7 going to be acidic, above 7 going to be basic. Now, as I mentioned before, the POH scale actually runs opposite of that, but it's still 0 to 14. Less than 7 is going to be basic, a greater than 7 is going to be acidic, and neutral is going to be 7 in this case. So if you have a low pH, you will have a high pOH and vice versa. So my recommendation would be I wouldn't even worry about the pOH scale and just really focus on the pH scale, which is what most people have in their head. The reason I pointed it out is when you're asked this common question, like you were asked before, is it acidic, basic, or neutral, the solution? There is only one answer for that. Yes, it cannot be acidic and basic at the same time. Although in a lot of exams and stuff, I've seen that given to me, it's acidic and basic at the same time. And the reason that happens is for this. People will calculate the pH and go, cool, it's below 7, it's acidic, and they calculate the pOH and go, cool, it's above, it's above 7, it's basic as well. Yeah, because they do those both. So my recommendation is I would probably not look at the pOH value. I would always look towards the pH scale because that's usually the one most people have in their head, and look at it and decide your acidic, basic, or neutral. Again, should only be one answer for that question. Yeah. I've never had anybody give all three, which I think is good, but I've definitely had people get both acidic and basic. Any questions on that there? All right. All right, so let's try it here. The pH of rainwater is 4.82. Let's just try out all of our calculations here. Let's calculate, like it says, the H plus concentration. Let's do the OH minus concentration. Let's do the pOH, and is it acidic, basic, or neutral? And for the bottom one here, we have an OH minus concentration of 2.5 times 10 to the minus 7. Let's also calculate the H plus, the pH, the pOH, and is it acidic, basic, or neutral? All right, so okay, let's take a look. So on the first one here, we are given the pH of 4.82. So since we're looking really to solve for everything, we do have a variety of ways we could approach it. I'm just going to go for, at this point, you really could get two things directly from this. You could get either the pOH or you could get the H plus concentration directly from it. I'm just going to go first with the pOH. So the pH plus the pOH is going to equal 14. That means that the pOH in this case would be 14 minus 4.82. And that's going to get me, looks like a 9.18 in this case. Again, at this point, you have a few options as what to do, but I'm going to go H plus next. Since I do have the pH, I could get the H plus directly from that by doing the inverse log of the negative pH. And again, when you punch that in on your calculator, usually on most people's screens, they'll kind of put a 10 and a caret up there. You do want to make sure you make a negative 4.82, and obviously a lot of times close parentheses. And if you do that there, you are going to get here, we got 1.5 times 10, looks like 1, 2, 3, 4, 5 minus 5 molar. Again, it does need a unit because it is a concentration. At this point, still opens up a couple of doors for you. You can go KW if you wanted to get the OH minus. You could also do the same calculation here for pOH as we just did there for the pH. So I'll do that one on this one here, I think. So we'll go OH minus will equal the inverse log of the negative pOH. And again, on your calculator, it will look something like this, 9.18 here. So we're going to go negative 9.18. Going to get us here, I'll go above it, 6.6 times 10 to the minus 10 molar. Also a reminder that if you are going backwards like we just did here, from like the pH value, which has 2 decimal places, my concentration should have 2 sig figs. Yeah. So again, it works in both directions as well. Same thing here, 2 decimal places, 2 significant figures in the concentration. At this point, you have a lot of things you can compare to determine acidic, basic, or neutral, but probably the easiest is just to take a look here. And clearly, since it's acidic rain, right, or acid rain, it is less than 7, so that's going to be acidic in this case. Any questions on any of those there? All right, taking a look at the bottom one, we have the OH minus concentration is 2.5 times 10 to the minus 7. Here again, you have two options. You could get the POH directly from this. You could also get the H plus using KW. So for old time's sake, I will do that. I'll go with my KW here to get the H plus, but you obviously could go the other way as well. And again, we get 2.5 times 10 to the minus 7. That is going to give me a H plus concentration here. Too many zeros to count. It's going to give me, I think, 4.0 times 10 to the minus 8 molar. Clearly here we could get the POH by just taking negative log of 2.5 times 10 to the minus 7. And that would get us a POH here of, looks like 6.60. Once again, two significant figures, two decimal places. Since I did get the H plus already, I could do the pH here is negative log of 4 times 10 to the minus 8. 4 to the minus 8, there it is. And that's going to get me 7.40. Again, two significant figures, two decimal places. Clearly here, you could have also done that the pH was equal to 14 minus 6.60. Get you there as well. So again, there's a few different ways that you could do it. They all should give you really the same answer. At this point here, I got a 7.4 pH. That's going to be slightly basic. Yeah, so it is above 7. Again, we're going to go 7 on the nose, pretty much is going to be neutral. Any questions on any of those calculations or how to calculate it? Yeah. Take a look here. An environmental chemist, rainwater was determined to have an H plus concentration of 3.5 times 10 to the minus 6. Let's do our normals here, pH, POH, OH minus, and again, acidic, basic, or neutral. All right, so in this one here, we have H plus is the 3.5 times 10 to the minus 6 molar. So I'm just going to go for the pH. So minus the log of 3.5 times 10 to the minus 6. That's going to get me a pH here of, we'll go 5.46. I could obviously get the POH pretty easily by taking 14 minus that number. And if I do that, we're going to look at it 8.54. And since I now have the POH, I could easily now obviously get the OH minus concentration by taking the inverse log of the minus POH. I could also use KW if I wanted to, which would give me something like this here. And that would get me, it's like 2.9 times 10 to the minus 9 molar in this case. Again, looking at the pH, that is definitely less than 7, so this feels acidic to me. Any questions on any of those there? All right, let's see. So acids and bases can be strong or weak, and they are basically electrolytes. So acids and bases, when they go into solution, they break apart into ions, and that is essentially what electrolytes are. Strong electrolytes are things that will 100% break apart into ions in solution. So if you have some sodium chloride in solution, when it's dissolved, you have 100% of these ions. You have none of the whole unit sealed together. If you had an acid like hydrochloric acid, which is a strong acid, it also will 100% break apart into H plus and Cl minus. It's basically all these guys here, 100%. You have none of these units together. That is why it's considered a strong acid, because when HCl goes for a swim, it basically just breaks apart into its ions. But because it will produce a lot of free H plus really quickly, just by going into the solution, is considered obviously a strong acid in that case. By the way, the list of some strong acids is kind of what we see on the bottom there, but it is definitely good to know. So your list of strong acids: hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, and hydroiodic acid. This list of 6 strong acids are good to know, and that is because based on process of elimination, if it's not one of those 6, it's probably going to be a weak acid. So it's a little bit easier just to know the 6. And then if it's not one of the 6, it's going to be most likely a weak acid. So hydrochloric acid, nitric, perchloric, sulfuric, hydrobromic acid, and hydroiodic acid. Not all acids are strong acids. There are weak acids, like acetic acid here. Acetic acid will set up an equilibrium, so we got our arrows going in both directions. Different though with a weak acid, which is a weak electrolyte, they mainly stay together. So in solution, you mainly have acetic acid. You do get a few of these guys produced. So if you took something like hydrofluoric acid, which is also a weak acid, and you put that into solution, you would actually mainly have hydrofluoric acid sort of guys still together. It will break apart a little bit into some ions. So since it's still able to produce some H plus in solutions, it's still considered an acid, but it's nowhere near as strong of an acid as HCl, which was just going to completely break apart and produce a lot of H plus really, really quickly once it goes into solution. By the way, as we'll talk about, that also will set up an equilibrium, which is a little different in terms of how you solve it. So our strong acids here, hydrochloric acid, again, would produce H3O plus in this case, as we do have the water as it sends the H plus over, plus some Cl minus. Same thing here, we will get H3O plus and nitrate. Here we'll get H3O plus and perchlorate. And here we will get H3O plus and actually hydrogen sulfate or bisulfate in this case. As again, the hydrogens do come off one at a time, right? In this particular case. These are all one-way streets, which means all these guys, when they're in solution, are going to produce a lot of free H plus really quickly in that solution. And again, that's what's going to make them a strong acid. Weak acids, on the other hand, as I mentioned, will pretty much stay together, but will break apart a little bit. So same idea here. We would get H3O plus and F minus, H3O plus and NO2 minus. H3O plus and sulfate. And H3O plus and hydroxide. So unlike the previous one, this is mainly what you're going to have. You'll have a little of these guys. So again, still able to produce some H3O plus or H plus in solution, but nowhere near what a strong gas can do. Bases as well are strong bases and also weak bases. Most strong bases come from group 1 and 2 on the periodic table and have hydroxide in them, like you can see there. Sodium hydroxide, potassium hydroxide, barium hydroxide. Essentially, if you go kind of on the periodic table there in group 1, like I said maybe earlier, lithium, sodium, potassium, hang a right there, calcium, strontium, barium. You kind of hook any of those to these guys up with hydroxide, you're probably going to end up with a strong base. Strong base, just like a strong acid, is considered a strong base because when something like sodium hydroxide goes in for a swim, it's going to completely break apart into ions and it's going to produce a lot of free OH minus in that solution, which is going to make it pretty basic in this case. Now, weak bases, on the other hand, are also weak electrolytes, and in this case, they're going to accept the H plus. Then you will get HF. You actually get back where it came from and hydroxide produced. Here you will get HNO2 and hydroxide produced. So they are still able to produce some hydroxide, so they're still considered bases, but a much weaker base than something like sodium hydroxide, just going to fall apart. Probably the most common weak base is ammonia, is the most common one that you come across. And again, it also is going to accept the H plus, which in this case will give you NH4 plus, and OH minus are ammonium hydroxide in this case. And again, it's able to produce hydroxide. Now, there's a really important relationship between acids and bases and their sort of conjugate partners. Now, when we look at the relationship between them, if we have, for example, an acid and its conjugate base, if your acid is a strong acid, it will have a relatively weak conjugate base. So if your conjugate base came from a strong acid, it's going to be relatively weak. If you have a weak acid, its conjugate base will be relatively strong. Now, its conjugate base is strong, but it is not a strong base. What we are actually talking about in this case is the ability to continue to react. So not necessarily strong in the sense that it will be a stronger base than sodium hydroxide. It is going to be a weaker base than sodium hydroxide. But what it has the ability to do, which we'll talk a little bit more about later on in this chapter, is, for example, it can continue to react with water and produce either H plus or OH minus and affect the pH. So it actually has the ability to kind of continue to react with water if it is strong. So this guy would have the ability to react with water and continue to affect the pH of that solution. Same thing with our bases and its conjugate acids. If you have a strong base, its conjugate acid is going to be relatively weak, which again means that it's not going to react with water. It's essentially neutral and will not really affect the pH of the solution or anything like that. If it is a weak base, its conjugate acid will be relatively strong. And again, what that means is it will have the ability to continue to react with water, and it will definitely affect the pH because of that ability to react with it. It again is not a strong acid like hydrochloric acid, but is strong in the sense that it will continue to react. H3O is the strongest base, strongest acid that you could have in solution, and OH minus is the strongest base. And again, there's sort of that opposite relationship between your conjugate acid and conjugate base pair. And that's really important when we talk about salts in this chapter and what happens with those type of things and how they react. Any questions on that there? So here's a table from your book, again, kind of showing that up here, strong acids, opposite end there, stronger bases, weaker acids. So that sort of opposite relationship between basically they're partnered on the other side. Yeah, basically what we got going on there. So again, a strong acid completely dissociates and a weak acid will stay together. So let's say, for example, we had given to us We want to know the pH of go with 0.6 molar nitric acid. So let's just say we are not given like just a generic H plus or OH minus concentration, but we're actually given a formula of an acid, which in this case is nitric acid. We know that is one of those 6 strong acids, which means when it breaks apart, it's going to break apart into H plus and nitrate in this case. And we know the concentration here is 0.6 molar. But if we wanted to calculate the pH here, we are definitely interested in the H plus concentration. So we do need to figure out the H plus concentration. And perhaps you remember from previous semester, when you're dealing with concentrations, you can kind of think of it like stoichiometry in a sense. It is a 1-to-1 relationship between those two, which means the concentration of the H plus is also 0.6 molar. It is also, by the way, a 1-to-1 relationship between that and the nitrate, which means its concentration is also 0.6 molar, not that you need it in this particular case. If it broke apart into not a 1-to-1 relationship, you need to multiply by the coefficient. So if it was like a 1-to-2, you would have to multiply by 2 and so forth. The reason that works is the long calculation is this of that, which is 0.6 moles per liter of nitric acid. You basically do like a stoichiometry calculation between the two. 1 mole of nitric acid gives you 1 mole of H plus. The moles of nitric acid cancel, gives you 0.6 moles per liter of H plus. So same concentration. But again, you could quickly do it just by doing 1-to-1 or 1-to-2, 1-to-3, whatever it may be. So since we know the H plus concentration in this case minus the log 0.6, and in this case, it looks like we'll get a pretty low pH there, I think. 0. We'll go 222 in this case, right? Which is definitely acidic, as that's close to 0 for sure in this case. So sometimes you may not be given the actual you may not be given just H plus or OH minus. You may be given a formula. You do have to look at it and see if it's a strong acid or even a strong base. If we were dealing with a strong base in this situation, the thing that we would be interested in is the hydroxide concentration, right, of that strong base, because the hydroxide concentration of the strong base would give us the POH, and then we could get to the pH, right? So if you could also do this with strong bases, except obviously you get the hydroxide, which usually will take you that POH to the pH sort of route. Any questions on that there? All right, so why don't you try a couple here? We got nitric acid, 2 times 10 to the minus 3. And we also have our strong base there, barium hydroxide, 1.8 times 10 to the minus 2. What is the pH of each of these solutions? Okay, let's take a look. So the first one there is nitric acid, which obviously is one of those strong acids. So we do know that when nitric acid is in solution, it is going to 100% break apart into H plus and nitrate in this case. So really for the pH, it is the H plus concentration that we're interested in. Um, So we have the concentration here that's 2 times 10 to the minus 3, and it is a 1-to-1 relationship between it. So we take 1 times 2 times 10 to the minus 3, and that gives us 2 times 10 to the minus 3 molar as our H plus concentration. Now we could go into our pH minus the log there of our H plus, and that's going to be minus the log of 2 times 10 to the minus 3 in this case, and minus log 2 to the minus 3. And that's going to be a 2.7 pH here. That does make sense since it is an acid, so that's an acidic pH here. If you got a basic pH, you clearly did something probably wrong in this calculation. Yeah. Any questions on that there? Take a look at the next one. That's barium hydroxide, which is a strong base. Again, a reminder, if you kind of go like we talked about a second ago, lithium, sodium, potassium, calcium, strontium, and barium. Again, any of these guys with hydroxide is typically a strong base. Usually most of those guys are in group 1 or group 2. So again, this will break apart. And when this breaks apart, we will get barium with a +2 charge, and we will get 2 hydroxides here. Now, in terms of pH, the OH minus is kind of important. That is going to allow us to get to the OH minus concentration, to the POH, and then to the pH. So we want to figure what that is. Here we have 1.8 times 10 to the -2. In this case, it is a 1-to-2 relationship between the whole thing and hydroxide. It is a 2-for-1 deal. You get twice as much hydroxide per. So you do need to multiply it by 2 to get the proper concentration there. And if you do that, you're looking at 0.036 molar. Now, going into our POH, because that is the hydroxide concentration, 0.036 in this case. Looks like a 1.44 in this case. And once again, that is the POH, not the pH. So we still need to take that last step of taking 14 minus our POH here. And that is going to turn us into a pH that makes more sense. 12.56, which is definitely basic. And this is a base. Questions on any of those there? So again, sometimes, like I said, you may just be given a form of an acid or base. So you got to determine, is it a strong acid or a strong base? And are a weak acid or weak base? And if it is strong, you basically just need to get either the H plus concentration or the OH minus concentration, basically from the formula. Any questions on that there? And here's again a couple of lists here from your book of some strong acids and strong bases. They're probably good ones to obviously know. Now, what happens with weak acids? Well, weak acids are a little bit different. They will set up an equilibrium because they're weak electrolytes. And because they set up an equilibrium, we could write our favorite thing ever, which is a equilibrium expression. We're going to take our products divided by our reactants here. And that is what is known as a Ka, adding to our big list of K values, Kc, Kp, Kw, now Ka. And it is still an equilibrium constant of products over reactants. Because it is still just an equilibrium constant, we still do not put in anything that's a solid or a liquid. It is still things that are aqueous or gas. And this is the equilibrium constant for a weak acid. And as the Ka value increases, the strength of the weak acid increases. So you have a stronger weak acid when you have a larger K value or Ka value. The reason for that is if I have a large Ka value, which is really just a large K value, that means when I reach equilibrium, I have reactants or products. If I have a large K value, I have. There you go. Thank you. So we have products, right? And on the product side, that is where we find our H plus, right? So if we have more products, we will have more free H plus in that solution, and it will make it a stronger weak acid than some other weak acid. It is still a weak acid. It is nowhere near as strong of an acid as a strong acid, but it is a stronger weak acid is the way you kind of think about it. So in comparison of one weak acid to another, the larger the Ka value, the stronger that weak acid is in comparison to another. It is still much weaker of an acid than a strong acid like hydrochloric acid or anything like that. Would we have a Ka value for strong acids? Should we have a Ka value for strong acids? The answer is no, we will not, because a strong acid is a one-way street, right? So there is no equilibrium that's going to be set up. And because there's no equilibrium setup, you will not have a Ka value for strong acids. So that's a very easy way to know whether or not you're dealing, for example, with a weak acid or not. If you see a Ka value in the problem or you see it in a table, it's a weak acid for sure. Strong acids will not have Ka values. The only strong acid that sort of has a Ka value that's not very helpful is sulfuric acid. Because it's a diprotic acid, it actually has two hydrogens come up like we talked about before. The first hydrogen and then the second here, which actually is a weak setup here. And for the first one, usually if you find it in a table, it'll just say it's really large, which is not very helpful for calculations. So typically speaking, strong acids don't have Ka values associated with them. And that's probably the only one in a table you might find, but it usually doesn't have a number either. It just says really, really large, basically. Yeah. So how do we solve weak acid problems versus strong acid problems? Because it sets up an equilibrium, we actually have to do a couple other things. Here's a table from your book of some Ka values, which you might need to reference as you're doing problems. And obviously you have our different acids through here. So how do we solve these sort of problems? Well, the way that we solve sort of weak acid problems is we want to basically figure out the H plus concentration. So actually, let's just go through that example there. Let's do that one. So let's say we have this example here of 0.5 molar hydrofluoric acid has a Ka value of 6.4 times 10 to the minus 4. First off, as soon as I see that, I know that this is a weak acid. And by the way, I also know it's a weak acid because it's not one of those 6 strong acids we talked about earlier as well. So by process of elimination, you also know it's a weak acid. So it will set up an equilibrium. Unlike our strong acids, it will come back both ways here, and we'll set up this equilibrium like so. So because it sets up an equilibrium, we actually solve these the same way we solve equilibrium problems, which is we do an ice table. So we will do an ice table here. We have initially 0.5, and again, nothing mentioned about these guys, so we will zero them out. The change here is going to be minus x, and plus x. And that means when we reach equilibrium, 0.5 minus x, and x. So here we have a little bit more work with a weak acid because it does set up this equilibrium. It's a two-way street, so you got things going both ways. Unlike a strong acid or strong base, which is just going to dump out H plus and OH minus, nobody's coming back the other way. So we already know what those concentrations are going to be. We will put this into our Ka expression just like we did in equilibrium, which would be our H plus, our F minus, divided by our HF. And that is going to equal 6.4 times 10 to the minus 4. Now, what are we really interested in this case? Unlike a regular sort of equilibrium problem where we might be interested in everybody's concentration, since we're interested in the pH, we're really just interested in the H plus concentration at the end so that we could eventually go into our pH equation and solve for our pH, right? So that's basically, the goal really of this ice table is in most cases just to get that H plus concentration so that you can calculate the pH. So to do that, we're going to do our same thing. So that's going to give us x squared divided by 0.5 minus x equals 6.4 times 10 to the minus 4. As we talked about last time, I see a small value of k here. So I'm going to assume x is equal to 0 because of my small k value there. And that means that I will end up with x squared divided by 0.5 is equal to 6.4 times 10 to the minus 4. I'm going to multiply to the other side, and then I'm going to square root it. And if I do that, I will take 0.5 times 6.4 to the minus 4. And then I'm going to take a square root of it, get you 0.00032. And then when you square root it, you get an x value of 0.017. I'll call it 9 in this case. Remember that when we do the assumption, we do need to check it. And to check the assumption, you take the value you got, you divide it by what you're going to subtract it from, which is 0.5, and you times it by 100%. And we are shooting for hopefully less than 5%. And in this case, we got 3.6%, which means the check is good here. So because that check is good, that would give us really what we're interested in, our H plus concentration. So the concentration of H plus equals X in this case, which equals 0.0179 molar. Now we have what we need to go into our pH. Our pH in this case minus the log of 0.0179. And I'm going to use the whole number on my calculator. So wherever it went, there it is. I can go 1.75 on that as our pH in this case. It is acidic, which is good since obviously it is a acid in this case. Any questions on that there? You want to remember that you definitely want to make sure you check it because again, it may not always work the assumption. So again, if the assumption doesn't work, you would have to go back and solve it some other way, which in our case would be more quadratic. Yeah. Any questions on that there? All right, we're laid up there for